Так, значит, мы продолжаем. I speak English, right? So, it's the second talk. So, let me recall briefly that the last talk, there was the definition of category data, simplicial set as a functor, or simplicial object in category E as a functor X. I defined realization of X where E is, say, set or top. Yeah, and then we have seen that the realization functor is left adjoint and it commutes with all coproducts, then as it implies, all coproducts. And we see the more deep, not seen, but I just mentioned that product realization of the product is product of realization, and moreover, realization commutes with all finite limits. Commutes with all finite limits. Well, also I defined the category gamma and defined an embedding I. Not really embedding, but some functor. So it's not correct to call it embedding from delta to gamma. Right, and and I'm going to, I talked a little bit about the functor gamma op to E, so which I'm going to use to define what Sigal gamma space is, right? So actually we will need some, absolutely not elementary technical lemma about what I call delta space, which I'm going to use for gamma spaces. So then let me mention it just now. So I recall that delta space is a functor from delta op to top, and such that x of 0 is homotopically equivalent to a point, and second that the functor, that the natural map from x of n to x of 1 in power n, which is given by what I call f1 times so on fn, which are actually operators from 1 to n, which sends I 0 to I and 1 to I plus 1. So then it's a homotopic equivalent. So then we need the following. So then theorem. Actually, it's, I would say that technically it's the most hard point in the Sigal paper about that. Although it's not for gamma spaces but for delta spaces, but he uses it for gamma spaces. So the statement is the following. So then if the first statement is if x1 is k connected, I recall that it means that pi I of x1 is 0 for I less or equal than k with any base point. Then realization of x is k plus 1 connected. This is the first statement. And the second statement is that we have, so then we have actually in realization, right, we have x1, realization 1, which actually comes from the simplices of dimension 0 and like that, and dimension 1. So then actually we have here
skeleton.
Huh? Skeleton. So there sits
one skeleton, right? One skeleton.
One skeleton, right? Yeah. So then actually, but in principle for x1 it's always embedding, but in principle in the proof, which I'm not going to reproduce, Sigal also needs that we have really filtration by closed embeddings by this skeleton. And this actually is rather complicated when we work with topological delta space, but not in sets. So then here some conditional next called redefinability actually is used, but for x1, I think in general nothing is needed. So then we have such a map, and then but actually we have a zero. So then in particular by relations, how I define the realization, right? In interval we have two vertices, say 0 and 1.
What is delta prime or delta? Is it just interval? Delta 1.
Delta 1 is what I called yesterday, so under some request I defined delta n as a standard n simplex in Rn plus 1, so then it's subset in Rn plus 1. So delta 1 is just, we can think of it as just a unit closed interval. Yeah, so it has two...
May I ask you a question?
Yes, please.
So you think what you call delta space?
Huh?
Delta space, I suppose that you actually, the data is quite finite, it's not all this, you don't need all this xn because they are equivalent. So, I mean, the data of this delta space could be defined in terms of something like x0, x1, and x2.
Not correct. It's like a nerve. It's like a nerve of category. It's like that. But you have actually not a nerve of category. You have just an arbitrary function.
The structure of space encodes higher coherence of composition of the space.
It's encoding an infinity structure.
You are right that if it was, say, for example, monoid, associative monoid, the example which I considered last talk, then all higher would be defined. Yeah, so then the data is up to 2. But in general, so it's something like model A infinity structure, right?
The mapping 2 is just a weak equivalence. It's not strictly an isomorphism. And so that's why there's you need extra data.
So anyway, in realization, I have a class in equivalence classes of this guy, right? Which I in the realization, and by the relations which I define. So then this, if I restrict it to this point and to this point, then it will be reduced to some point of x0, right? It is some point of x0, and homotopically I have a single point in x0. So then it means that actually it is glued to the reduced suspension. So then suspension of x1 is mapped to the realization by just very simple reason. Yeah. So then, so then we have that, and it defines an adjoint functor to loops on the realization, base loops on the realization, and the second statement is about this functor. Yeah, and this second statement says, so I move to here, and this second statement says the following, that if x1 is group-like, this is terminology which I actually, maybe I used different terminology last lecture, but it means that the monoid structure on pi 0 of x1 is a group. So I explained that we have something like x2 to x1 times x1. This is homotopically equivalent. D0 times D2, this is D1 x1, and then we have a monoid structure. So it's so it's group-like. If it's this monoid, it's a group. This is just terminology. And so the second statement says the following. So it says that if x1 is group-like, or x is group-like, which is the same. Yeah, probably better to say that x is group-like. Then this map from x1 to omega realization x is homotopic equivalence. So this is actually, the first statement is not very hard to prove really, but the second statement is really very technical, I would say, because it has some simple cases which I included. So, well, maybe I will...
I think you said reduce suspension, so you like cap off and then...
What?
You said reduce suspensions?
Reduce suspension,
So
right.
you kind of make a cylinder, you pinch both ends and then you glue the two ends together?
I guess so, right?
But doesn't that mean that x has to come with the preferred base point? Where does that come from? Not at the homotopy, but really...
No, but we have a base point. Yeah, indeed. So we have not really. Yeah, I mean, if x0 would be a point, then it would have a base point. But in this case, okay, let me say just suspension, not just suspension, like that. Yeah. So anyway, this is yeah.
And, speaking about reduced suspension, you do not glue, you contract the.
Yes. So then actually.
You do not glue these points, you contract.
Yeah, well, I mean that by relations which I impose in the realization, we can look at this as a cylinder over x1, and then by the relation it follows that these two upper and lower faces are contracted at least homotopically. They are not properly contracted because if x0 was a point, it would be properly contracted, but now it's homotopically contracted, so it's homotopically suspension, right?
But x0, xn, etc. are pointed spaces or not?
Huh?
All the spaces.
It's contractible topological spaces.
No, all the spaces are pointed. The functor from the.
Well, typically not.
Not okay. We do not require the.
No, well, if x0 was a point, then it would be automatically pointed because then
by the inclusion of x0.
By not inclusion, but by degeneracy maps. The image of degeneracy maps would give you a point in each this xi. But now, well, it's something like. Yeah, I mean that we have unique map from n to 0, right? It's 0, it's a final object in this category delta. So then we have a contravariant factor, so then this degeneracy map would give you a point in each xn, but now you have something like homotopy point, it's fat point, right? Because it's, this is what I meant. So then in particular for x1 you have, well, something which is homotopically suspension, and then you can consider a joint map, and then the statement is that this joint map is homotopy equivalent under some assumption. So then for the first statement I can a little bit for the first statement, well, I will not provide you really proof because it's details are complicated and technically complicated. But first statement is not that hard as the second. So then the idea is that we have some filtration by, as you say, by Skeleton. So if we had really simplicial set, it's properly like that. But if we have a simplicial topological space, we need to impose some condition like critical vibrancy to have closed inclusion. So we assume that it's closed inclusion, so then it follows, if it's there closed inclusions, it follows that homology of X is column of homology of Xi, and then so this is we are fighting for to have closed inclusions, and then we can easily deduce that Xn quotient by Xn minus 1 looks like a suspension homotopically as suspension of x1 times x1 n times. Yeah, well, and then we, in particular, we see that x1 quotient by x0 is homotopically suspension of x1. So then, if x is x1, it's so here it's, here it's just like that, I guess, right? Here it's without this, so just x1. Yeah, so then if homotopically like that, so then if x1 is k connected, then it follows from here that that x1 is k plus 1 connected, yes? Well, and then one can prove that, we actually use something like Gurevich theorem that if we have, meaning that we can compute homotopy groups as homology groups if some first groups are vanished, and then and if it's connected at least. So anyway, everything is reduced to this computation, and then
it's really weak equivalence.
Weak
equivalence in the weak sense.
Yes. So then it's k plus 1 connected, and then the pieces which we glue further are more than k plus 1 connected. So the next one, I guess it's something like k to k plus 3 connected, if I'm not mistaken, and so on. So then it actually from this we can conclude that, that connectedness increases by 1 after taking realization. But the second statement is indeed complicated, and the second statement has several simplest cases. For example, the first thing is that when M is a monoid, yes, just a second. Yeah. So if M is a discrete monoid, so just monoid in sets, yeah, so then we can take what I call BM. So it means that we take this, what I call XM, which we can also say denote as nerve of M or whatsoever, or rather category with one object with morphisms M. Yes, a monoid is a category with single object, and its nerve. It's what I yesterday denoted by XM, and then we take its realization of this nerve.
What is simplicial set?
Huh? Nerve is simplicial set. In principle, if I will have time, I was planning to define nerve of category. So, well, in principle, I'm not going to assume that people know, but this I defined yesterday explicitly, so then I can use it. This is by definition is denoted by BM. Yeah, so and then we know this is a classifying space in the case of groups, and then it's well known that we have actually some map of which actually, yeah, we have this, how to say, we have actually my preference to denote this nerve of M, so I would call it like bar of, maybe it is my favorite notation, because, and then I also have bar of M point, so which means that this is simplicial set. This is which I defined yesterday. So the nth component in M in times n, and here nth component in n times n plus 1, and then we have, yeah, we have something like so we had, well, the difference is that yesterday we defined it in components Mn. And then we defined all boundary maps, but here we have M0, M1, so on, Mn, and projection is projection along the first factor, right? So the map from, so that I mean that this bar M point is mapped as simplicial set to bar star M point. And this is actually projection along the first component. But here the differential D0 just drops M1, right? And here it doesn't drop, but it takes D0 here of M0, M1, so Mn is defined as M0, M1, so M1, M2, so on Mn. Yeah, well, we can maybe define it a bit less explicit and more accurately, but this is clear. So then, actually, if G is group, if M is group.
So in the last line, like this is the extreme differential for this new simplicial set called bar MM star.
Yes, exactly, and all other components are defined exactly as for this one. So the difference is only with D0. So high D, Di are defined exactly well. For example, D1 here of M0, M1, so on, Mn is Mn is defined as M0, M1, M2, so on, Mn. So exactly, and so on, right? So and the last one drops, projects along the last component, last fact. Okay, so then if M is a group, then actually the map of realization, so the realization of this bar star M star, okay, let me call it just M, like BM, and realization of bar M star is called EM. In fact, it's actually sort of sort of bar complex, like so this one is actually bar, I mean it's analog, it's proper analog of bar complex of say associative algebra, for which we know that it's contractible if algebra has a unit. So the same argument works here, so this is always contractible for any monoid with unit. Well, it's even more general statement exists that for any monad or so contractible. And it's actually proven as similarly to the bar complex of contractibility of the bar complex of algebra, namely you use some homotopy, but now you use not homotopy in the sense of complexes, but a bit upgraded to simplicial homotopy, but it does the same, it puts element 1 on the first place somehow.
If you replace star, the last star also by m, what would be the realization of bar complex?
It's something like, I mean, algebraically it would, this is quite difficult to say, but, well, here, here it will be contractible for anything here if m is here. But the realization is that I guess...
I said when you put m.
Yeah, it will be still contractible. You can put even a here, any a whatsoever.
Shouldn't that be m? It's like m cross m quotient by m.
Something, yeah. So then anyway, this is contractible for any monoid, and the proof is just the standard proof that bar complex in the homological algebra sense of algebra with unit is contractible, right? So it has zero homology. All homology is zero. Yeah, so this is similar statement, and but you should little bit upgrade the known proof because you should define what simplicial homotopy is, but this is only difference. So then anyway, we always have a map from here to here, so from EM to BM, where this space is contractible, and it turns out that if M is a group, then we can think of this map as a vibration, safe vibration, right? EM, BM, well, even if it's this G and G, so well, even, yeah, I guess actually, yeah, we can prove it, yeah, well, there are many ways to prove it, but for monoid it's not true that it's a vibration, well, any sort of vibration. So then we have the following thing, that we have self vibration for a group, self vibration, and this is contractible, and the fiber is G. As clear from this formula, because the fiber it's actually M0, right? So the set of M0, which is M, in this case of G, it's G, so then it's a discrete space, so this is sort of covering, I would say, a universal covering. So then particularly it shows on BG it's KG1, right? It's basically about that. And then
If G is discrete.
G is discrete.
We're talking about discrete.
I said that it's discrete,
Yeah.
I guess, somewhere here.
Yeah, M is the discrete moment.
Yes. So then, and where I wrote it?
Discrete monoid.
Discrete monoid, right. So then it follows that actually G is loops of BG. So, but actually G, it's exactly my x1 in this situation, right? For first component. So then, this is actually a very special case of single statement, the most elementary one. So then if it's x1, it's really a group, discrete group, then we can see it rather elementary. The next case is that when x1 is topological group. This is a bit more complicated, but it's also true, and it's proven via the quasi-vibrations, right? The technique which was invented when people proved Dold-Thom theorem of quasi-vibration. So then this is, so let me erase something. So then this is, yeah, I just mean that this statement is rather complicated actually, the second statement. And even for topological group, there is something to prove. It's not that elementary as this one. So then, yeah, so the next case is topological group. Yeah. So then we still have the same stuff, bar G1 to bar, G, and this is actually what we call XG. The last lecture, right, which is a nerve, which is the same that nerve of the category with one object, and morph is G. Yeah, so then we actually want to prove, so this is still contractible, this is the same. This is actually a general fact for any topological monoid. It doesn't matter. The only what matters is that monoid should contain U. Yeah, but then we have to prove that realization of P is a sort of quasi-fibration in this case. So I'm not going to go in detail, but well, it's something to do. Actually, it's not as immediate as that one. So then I mean that this is even more complicated, the second statement, because this is a particular case, but also something more complicated, where it's not topological group, but topological group in a infinity sense. So then I just stop this discussion on this theorem. I just want to show that we are going to use it. So what is most important for us actually is that, that we actually are going to use both statements, right? And also, if you remember, first lecture, I introduced the category gamma, which I am switched to now. Yes. Yeah, and then let me do the same explicit construction to motivate the further discussion as I did for this xm. So then I mean that here I recall that for associative monoid M, I constructed xm, which was a functor or even delta space from delta op to, well, top, say, right? If it's topological associative monoid. Well, then let me consider now commutative monoid, associative, of course, commutative topological monoid, and then I don't know how to denote it. Let me denote it by am, which is from gamma op to top, and I'm going to define such a functor, and this is actually the motivating example. Well, so somehow it's like that its value on n, it's also m in power n, but now we have to define all these operations, which I recall that operation that morphism in gamma from n to m well, even if I write maybe S and T, it's better to, as finite sets, then the mapping morphism in gamma is assignment from S to all to set of subsets of T, including empty subset, such that theta, if I not equal to J, then theta of I is disjoint with theta of J, and the union of this theta I may be not entire T, right? So then I'm going to construct out of such theta a map from m in power m to m in power n.
So you told us though that gamma op had this other description in terms of pointed finite sets.
It was gamma op.
Yeah,
right.
But you're also defining a functor out of gamma op. So why not just tell us what?
It's also possible, but well, I mean, in principle, let me do it in this way. Well, I think it's quite.
Okay.
Yeah, because actually we will see at least explicitly where we use commutativity in a very explicit way. So then I prefer to do it in this way. So okay, so then so then if we have m1, so on mm, sorry for double use of m. So then it is sent to x1, so on xn, where xi is a product in the sense of monoid, so let me denote it like that, of all mj of j in theta of I. So then I take the product of all, so then I have some element I here, and I have to define xi. So then I take the set theta of I. So this is set of, in my notations in M, subset of M. So then I have several of elements which belongs to this theta of I. And then I take the product of all these guys, and the order is irrelevant. Yeah, and if it's not empty, and if theta of I is empty set, I just say that xi it's a unit of my conductor. Yeah, so this is a construction. We see immediately, of course, so this is very similar to what we have in this XM. Moreover, moreover, if you take this embedding delta to gamma, then the restriction of this guy is exactly my XM constructed in the last lecture. Yeah, so of course it's a gamma space in the strong sense, so then I mean that here, if I take AM in N, then this is M in power N, right? So then it's in AM in power 1 in N, so then it's it's actually the same stuff, right? So, well, maybe I have to be more precise how I define these maps for any gamma space A, how I define map from AN to A1 in power N, right? So, well, but I guess it's quite clear. So then I take element 1 is sent to, is mapped to element I, just I, which is subset of N. One element subset of N, and then this is how I define. This is actually analog. If you remember how explicitly this embedding is with elementary intervals I told the last time, you will see that it's exactly the ith elementary interval in the ordinal, so it's exactly how I define this. Okay, so fine. Yeah, so this was very nice, and another story which I want gradually to go to the main topic of this thing. Yeah, so well, last time I said that there are two features. So one feature is that Bm is again for M topological commutative monoid. Then Bm is again a topological commutative monoid. And then we actually can take B of M and so on. So that we can iterate this construction, and in each step we get a topological commutative monoid. And as we know, there is M to omega 1 omega of B. So well, we have better to say sigma of M to Bm, right? Which we discussed here. And this gives me actually a spectrum. So then I have x0 equal to M, x1 equal to Bm, x2 equal to B of M, and so on. And the spectrum map, so then xi sigma of xi to omega of
Do you really want to mix sigma and omega?
Sorry, xi plus 1. Yes. So then it's defined in the similar way. So, and then actually, so we get a spectrum. And of course, it's the spectrum, it's not very interesting because I recall the theorem that any connected, at least, any connected commutative topological monoid, it's actually weakly equivalent to the product of over n of k pi n of m n. So there is such interesting theorem that if monoid is strictly commutative, then it's product of Eilenberg-MacLane spaces. So then in particular it's easy to write down what the homology theory. It's actually omega spectrum if, at least after group completion. So anyway, this is some simple spectrum, right? So, but I stress that
These are the ones that come from homological algebra, from chain complex.
Well, this actually, I guess one proof can be found in first book, concise, not more concise, but concise algebraic topology. Well, in my opinion, it's somehow related with, as far as I remember, with the Dold-Thom theorem. So then you can, so the Dold-Thom theorem is something like phi I of this infinite symmetric power of topological monoid. So, well, I mean, the commutative monoid, topological monoid generated by this M is reduced, I guess, homology, is homology group of M, and from that somehow we can split. Well, actually, I forgot details, I did not prepare, but it's somehow, I guess, the proof which I once learned uses this statement, which is Dold-Thom theorem. In fact, it's actually motivation, as far as I understand, for Quillen general definition, what is homology theory as derived factor of the abelianization, right? So this is actually, if you, well, you have...
What is written here?
Yeah, you somehow take all symmetric n power of m as topological monoid, and then you should identify units in all this guy. So you should actually take some little equivalence by gluing with units, and then you get something like that. So it's actually
it's like the space of just the sets, or like finite sets of elements of M, but like they are also like have topology.
Yeah.
It's topology, of course. Topology. Yeah, so then anyway, well, it was just, it's not what I'm going to talk about in detail, but it just somehow that as far as I remember, this fact for strictly commutative monoid is deduced from Dold-Thom. Well, but I like to stress that for not strictly commutative monoid, but what is called com-infinity monoid or E-infinity, which is the same for any sense, it's not true, because of course infinite loop spaces are not necessarily products of KPM. So then for commutative world, in difference with associative world, strict commutativity and weak commutativity, even up to higher coherences, are totally different issues.
So like, for example, if like we take like the second loop spaces, so like if we consider like Moore loops, right? Like it will be only commutative up to homotopy, and
it's not it's second loop space. I mean. But you can, for example, take the spectrum for topological case theory, and then it's for unitary group, and then it's infinite loop spaces, of course, as we know, but it's not a product of KPS.
I just want to say that second loop spaces are like not like that, right, John?
No, it's infinite loop spaces like that, like com-infinity. But I said the following, that for associative thing, A-infinity, like loop spaces, right, of Y, is first loop spaces. It's the same, it somehow the same.
It could be strictified up to homotopy.
Yes, so well, I mean that it's some, so then, I mean that in commutative world, there is a striking difference between strict commutativity, if you like to describe the homotopy type of the strict commutative monoid, which is not like that, or if you have weak commutativity in any sense. For example, as I defined the last lecture, like infinite loop spaces.
I mean, I just want to say that like this is like an example of this, right? Because like it's literally a topological monoid, like have more loops, but it's like this is like the only difference.
It's
that it's commutative.
It's not commutative, homototically commutative. It's yes. Okay. So let me go further. Sorry, because this is, we can discuss it after the lecture if you like, right? We can discuss it. Yeah, so then actually, so then you see that for commutative monoid we get a very simple way a spectrum. Maybe I have to recall that we use here that M times M to M is a map of monoids. So, well, I briefly told it the last lecture at the end. So then we can pass to this here. We use commutativity, right? Because for associative monoid, it's not necessarily map of monoids. So then passing to B, we get again a monoid which is commutative and so on. So well, and I like to see what we, how we can see such sort of phenomenon for more general gamma spaces, which are thought as common infinity, right? So then I like to construct in a similar way a spectrum from a gamma space.
This here is kind of n space, is a 10 space.
Just let me first erase, otherwise I cannot focus. So please, yeah, sorry. Huh?
No, I mean, you know that, right? Commutative groups of spheres are complicated.
What was the question? Okay.
I don't know what the question was. The answer is.
Okay. So let me introduce first terminology that if I have a functor A from gamma op to top, well, I use the following terminology that it's and such that A of 0 is homotopically a point, then it's called gamma space. Only that. That gamma space is special. So this terminology, which was introduced in Busfield Friedlander paper, and now it's conventional. If AN to A1 is a homotopy equivalence. By the way, it's the same stuff as to say that M plus N to A of M, which you can easily define to A of N, is homotopy equivalence, right? So these are equivalent statements, because you can take both to A1 in power N use plus N. So if you know that these two are homotopy equivalent, then this two also is, right? So then it's special in this case, and very special if it's special, special plus group-like.
Can you take it and before Siegel?
Huh?
I remember in Siegel's paper there was this. In Siegel paper.
In Siegel paper there is not such terminology. Siegel defines gamma space as special, and he called very special group like gamma space. So then in principle it's quite important, well, for constructions it will be quite important to construct gamma spaces even without this condition. So no, actually it was, I guess it was, well, Siegel paper, well, it's actually many places, well, it's not, well, there are perfect ideas of course, but technically it's written in such a way that one should spend a lot of time to understand how to fulfill details. Yeah, and Busfield Friedlander did it completely using model category language. So then I like partially in my presentation, I partially use what Busfield Friedlander did, but I am not going to use seriously model category, so even anyhow. So then basically I will follow Siegel approach, but well, with one difference which we will see today. Because yeah, I will mention explicitly. So at one point I will use approach of Anderson, which also worked on that, but at the same time.
To say the definition was in the Siegel space, but terminologies from the.
Yeah, definitions in the Siegel paper, but terminology that it's gamma space special and very special is Busfield Friedlander, exactly. Yeah, so then we have a functor from gamma to gamma to gamma, which I briefly defined at the end of last talk, which takes M and, well, even that, or we can take S to T, we have to S, well, ST takes to product of ST, and one can easily see that if we, for example, have a morphism from S to S prime and from T to T prime, in this sense that it gives us, well, ST to P of S prime T prime, where we take element ij to P, well, how to say, theta phi, we take it phi of I times theta of j, no, theta of I times phi of j. Yeah, and then it's actually a functor, and it's actually very essential.
ST goes to S cross T.
Well,
And
it's written, I guess, everything.
what is it? ST goes to S cross T.
Times T.
Yeah, it's a morphism from S T to S prime in gamma. S prime T prime, which explicitly is such a map.
No.
From-
I mean, what is written up there? Third line.
A pair of sets,
Three,
set.
Here, pair of sets, so then pair of sets, this is the object of gamma times gamma, it's pair of finite sets, is mapped to the product of their sets, or even if you prefer, m element and n element sets are mapped to m times n element sets, and the morphism I defined the natural way. So now it's quite, well, maybe I have to mention that for delta such thing does not exist. So, because then such maps, if you like to see what happens on delta, then such map would well, does not exist. Because then it would change the order, it would not respect the order. So in delta everything should be ordered, and this map actually assumes that the order is not, shouldn't be, needn't be respected. Yeah, so then, okay, so then if you, why I say, so I say that this construction actually gives me for arbitrary gamma space some mimic of, well, this construction of infinite spectrum in the following way. So let A be a functor from gamma up to top, then I can consider it as precomposing with this map as A of, well, gamma, for example, up to, let me denote it still A, to gamma up and then to top. So this is somehow, how to say, kappa. Yeah, so then, in particular we can take the, if you take realization, so then we can define it as A n m or n times m, no, n m, where these are two objects. So then we can take realization of that by n in gamma, fixing the second argument n untouched. Yeah, so then it's something like B, well, it's realization of A depending on M. Yeah, so then we can iterate this process, and actually this is a proper analog of this construction. Well, we can see it in fact. So this is very nice. So then actually for weak, not for strict commutative monoid, we argue in that way that this structure map is a map of monoids, but for weak monoids in the sense of gamma spaces, we make use of this function. Yeah, so then we get, yeah, then if we have some, so then let us assume that A is a special gamma space.
What is the name of this functor? I can't read it.
I think Siegel functor.
No. You used a symbol.
I guess sometimes it's called assembly or something, no?
No, but the symbol. There's a symbol. What is it?
Kappa.
Kappa.
I guess so.
Okay.
Yeah, at least kappa, because I never used kappa. So I use kappa for some special task. So this is a special map, so it's not TF and so on. Yeah, so then, so then in principle, if I now assume that, yeah, so first of all, let me make some remarks then. Yeah, so I use the same notations as for commutative monoid. So then when I iterate this process, I call it, say, B. I have A1, B, well, maybe, yeah, BA, then B square of A, and so on. And then we get a spectrum. And now, actually, if A1, so A1 is, yeah, so then in particular BA is always connected, right? Because well, it's actually clear just directly, but in principle, because A1 it's not, in general, A1 is not assumed to be connected. Not assumed connected. in general, but if it's, yeah, so then BA is connected, B square A is 1 connected. So this is x0, this is x1 spectrum, this is x2, and so on. Yeah, so then we get what's so-called connective spectrum, right? Connective spectrum, because xi pi I of xn is 0 for I less than n. And it follows from this technical statement which I started with. And also if A is group-like, so then look, like actually the maps from BA to omega B square A and so on, B square A to omega, B cube A and so on. These are always homotopy equivalences from this technical Sigal statement because BA is connected. BA is connected and therefore it's group-like, right?
But in the Sigal, I want to understand this. In the Sigal theorem, we not only ask to x0 to be like contracted.
No, it's not.
We are asking to this like multiplication things. How to apply this?
Yes, you are right. Maybe I have to be more precise. So what I call BA, for example, is what I call B square A. Yeah, what I call BA is gamma space. Gamma space where as a gamma space. So how you define it? So then by m, right? So when m is equal to 0, it's still point, right? So because then if I take a product with empty set, I get empty set, and then it's actually the 0 component of this. So then I have space of m, the gamma space, right? Which is defined in this way, right?
Okay.
Yeah. So then for m equal to 0, it's still a point. Still homotopically equivalent to a point. For m equal to 1, it's exactly BA in my formal sense. So then BA, B square A, and so on are the first components of the corresponding gamma.
Okay, but even in the first step, is it true that A equals to loops of B?
Not always, because for that I have to assume that it's group-like. So then A. So this is some special condition. It's not always.
BA already group-like and then...
Because group-like means that pi 0 is a group.
Yeah.
By pi 0 in this case it's a single element. It's always a group. Because BA is connected.
Yeah.
By this increasing of connectedness. But for BA you can see it by hand. So then it's not a hard. Because now if you see how you define BA, it's something like, yeah, even if monoid is not connected, then you regard it as a category with single object and take the nerve of this nerve of this not connected category will be this single object will be connected, right?
Yeah, but
it's clear because it's because actually this if M was not connected, right? If not connected monoid, then when you take say this what is XM, or if you like bar star M star, and if you have some realization of this, which is called PM. Yeah, so then actually as a simplicial set, you have a point in degree 0, then M in degree 1, so then this not connected thing is now not in degree 0, but in degree 1.
Yes.
So then you should take the product of this one with unit interval and glue the ends with this point, and then glue further something. So you get a connected thing, right? So then, well, it's actually precisely it follows from this more general Sigal theorem.
But I want to understand that in Sigal theorem, one of the conditions are that we have this isomorphism of x or like am to a1 times m.
Exactly. Yes. We have to. Yes.
And how we get it? How we get it here? Like,
this is very
because of this construction for functions.
Thank you very much. Because I agree that well. Because I actually changed the written note. I now do it somehow more chaotically than I planned. Then actually I forgot to say that. This is a very good question. Yes. It's very good question. So you are right. So
It's
I
by
have-
this factor couple. or not?
Yes, exactly.
Okay.
I agree with you. So then I have to prove that this stuff actually the map to dA of M to dA of N is a weak equivalence, right? To be able to apply this Sigal theorem.
Okay.
Yes, exactly. So then how I can see it, because now this is actually, so then, so this is actually quite simple, because this is just, let me see. Yeah, so just a second, I will have a look. Yeah, so, yes. Yeah, well, so you have, you look, we use two facts, right? We use that Sigal works with good space, simplicial spaces, so it means that we use that if x and x prime is component-wise weak equivalence, then it follows that realization of x to realization of y is also weak equivalence. This is actually also subtle point for which we need either to change the definition of realization as Sigal does, or to impose the assumption that it's redefinable for topological space. So this is, well, for simplicial sets, it's always true, of course. Because this is meaningless to say that the components are just sets. But for topological simplicial, simplicial topological spaces, it's not automatically like that. So because so there is some technical assumption which it's not automatically. But we assume that all our spaces are good, or even as Sigal does, we change the realization by some, well, homotopically, the same for good spaces. Yeah, so let me skip this point, this I assume. Yeah, if you like, I can talk about that. You can ask me after the lecture, right? So then the second thing which I'm going to use that the product, that the realization of x times y is homotopically equivalent even for topological case to realization of x and realization on y. Okay, so then now if we have b right, so then we can argue as follows. So then we have am times n1, say, times m. And then we have, say, n equal to n1 plus n2, n2, and then if we have n1, so then we have a map from A of n1 plus n2 times m to n1 times m to A n2 times m, just because here the union of these two sets, it's actually this set, and as I explained, it's weak equivalence. Sorry, actually what I'm going to use is something different probably. It's m here and m1, m2 here, sorry. Yeah, n here and m1 plus m2 here, and then actually m, it's m1 plus m2, right? So then I have, this is weak equivalence, because as I said, for gamma set, if you have union S and C, then the canonical map to A of S to A of T is coming from canonical inclusions. And C to S union with T is disjoint union, are weak equivalences, right? Because they are all projected to A1 in number of elements of S plus number of elements of T. These are weak equivalences by assumption, then this is also weak equivalence. So then for any disjoint union of sets, we have such a weak equivalence, and this is a form of speciality condition which I'm going to use. Now here we have we somehow take n times m1 plus m2 element set, and we represent it as disjoint union as n m1 and n m2 element sets in this way. So then I guess that I see that the canonical map is homotopy equivalence. Yeah, so then now when I consider realization, I should take realization by n. So then what I have actually, look. So then realization of yeah, so then actually here I have actually the product of two simplicial sets, right? I recall that the product of two simplicial sets is defined as xn times yn and arity n. So here I have the same n, so it's just the product of a m1 times a m2 as simplicial sets by this argument. It's just a product. So then the realization of this is homeomorphic to realization of a m1 and a m2, right? Yeah, so just homeomorphic because of this property. So and this is exactly actually, and yeah, so then what I get, right? So and this is homotopy equivalent, right? And this is because I use that this maps are homotopy equivalent, and this is homotopy equivalent to a realization of a m1 plus m2. So then for any fixed m1 and m2, I have by variable n, I have this homotopy equivalence of simplicial sets by n. Then I use this sort of reading covariance whatsoever, saying that if I have component-wise weak equivalence, it gives me weak equivalence on geometric realization. This I make use here, and here I use just the standard fact that this is a product by n, it's product of two simplicial sets, and realization of the product. So that actually it's again, it's very good question. Actually I prepared, of course, but somehow I forgot to tell. Thank you very much.
Once again, did you say that this weak equivalence to a1 in the power of s plus t is by the, what did you say, by
I just look to replace this condition, initial condition, to this a priori slightly more general condition.
Okay, but we are given this weak equivalences to a1, always something.
For a we have, yeah, this we have, right.
We have by the data.
This is weak equivalent, this is weak equivalence. It follows that this one for arbitrary s and t, it's also weak equivalence.
So we choose a such that this.
No, the first one is special. Yeah, the initial a is special special gamma space.
Initial a.
Initial one is special. Your question, as far as I understood it, was that I have to argue that after I apply this construction and consider B as
going to be again. Right?
Yes, and this I think I proved.
Yes.
Yeah. So then I can apply each step. I can apply this technical Sigal statement, and then I have that it's.
I'm sorry, can you write the definition of BA again, like the formula, like, which was like erased?
BA of M, what, this one?
Yeah.
Yeah, then it's actually, I consider A of Mn times M in the sense of this map, right? And then I take realization of it by N in gamma. So then, I mean, as a functor on N, it's by functor, right? So it's actually gamma op. It's a functor from gamma op to top. So then I can fix M, it's the second argument, I fix it and consider it only as a functor by the first argument and take realization only by the first.
So like, it's also true that like I can write like ну черточку вместо n подчеркнуто написать, да, типа вот.
Где?
В скобочках А, в скобочках n умножить на m. Вместо n там черточку можно поставить, да? Это тоже...
Здесь или где?
Да.
Ну так я же поставил черточку или что?
Нет, не в смысле подчеркнуто n, а в смысле здесь аргумент, типа...
Ну это аргумент, да, то есть это вот объект гамма-оп на гамма-оп.
Сбивает с толку, что в названии просто, то есть специального топологического пространства аргумент уже подставлен внутрь, типа...
Нет, ну вот смотрите, у меня есть, look, I have a functor from gamma op times gamma op to top, then I can fix any object of the second component of the second gamma op, and then I get a functor by the first gamma op, and I can realize it as a functor. And of course, after realization, I get a functor by the second argument, and then here we see that if A was special, then this realization is again special as gamma space. So then it follows that BA in particular that we can apply indeed this Sigal statement, and this, and so on, these are always homotopy equivalents, but it not always, but only if A is group-like, right? So then if A is group-like, we have an omega spectrum, and if A is special but not necessarily group-like, so if A is very special, I mean, we have, well, always omega spectrum, but if A is special but maybe not very special, we have almost omega spectrum, so it means that this map x0 to omega x1 is not necessarily weak equivalence, not necessarily weak equivalent or homotopy equivalence, but x1 to omega x2 and so on are weak equivalences, right? This is actually the story. So then, yeah, then actually we have this spectrum, and what Sigal does, what he essentially uses, in fact, he uses another formula, explicit formula for Bn of A. And because this is quite unclear stuff, so how we can, well, we have some iterative realization, so then what it is more explicitly. And Sigal has a beautiful formula about that. And this beautiful formula, I'm going to explain it now. And this actually, well, actually, look, as I said, that for realization of simplicial set, we have x, right? For x from the delta op to say top simplicial space, we have some formula like top from realization of x to y is homotopy equivalent to simplicial top from x to singular of y, right? So which I defined the last time. So here we have actually, here you look on this, think of the spectrum as sort of enhanced realization. So then here, well, I mean spectral realization. So then gamma space A produces a spectrum, right? So A1, B, A1, say B square, A1, and so on, which here you can even erase 1 if you like. So this is a spectrum, which, as I said, if A is special, it's omega spectrum maybe except the first place. And then in general, even if not special, it's some spectrum, right? Even if A was not special, I cannot then apply the technical statement, but I still can apply this iterative procedure, and I get a spectrum even without assumption that A is special, right? Yeah, so then for any gamma space I have a spectrum, I would say. Yes, with some better properties if it's special or very special. And then I like to have, that spectra of this, how to say, I don't know, say B of A, this is a spectrum, I denoted BA. Yes, and here I take some other gamma space, say, L, it's another gamma space, it's another spectrum, Y maybe, Y. It's another spectrum, Y and spectra. Yeah, so then I like to have some adjunction that is something in gamma spaces, like from A to some functor applied to Y. Yeah, so this is actually what I like to have. Something similar to that one, and that's to this table in that sense. And to get such a junction, to define this f of I, I need some formula for nth term of this spectrum, which is more beautiful in a sense than this iterative construction. So I'm going to explain this formula. So I guess we are 15 minutes later, right? So then
Chairman is in the corner.
Well, I think you can use another, you're 17 minutes late, so I think you can use 17 minutes, so I'm finished.
17 you say, right?
Yeah, 17, yes.
So I start in 17 minutes. Yeah, okay, thank you.
So this functor f is going to be loops infinity?
Huh?
Is this functor f basically loops infinity? Then
Yeah, basically it's loop infinity in group like K. Something like something like loop infinity, but let me tell it later, right? So okay, so then actually the formula is the following, that now I just give a statement without explanation and then I explain. Then there's a single formula that I will explain now what does it mean. It's n-dimensional sphere, and the meaning of this sign I'm going to explain. Yeah? So let P be a based topological space. Based topological space. Then we can get gamma space, so Sn point. Then we have P point, it's a factor from gamma to top. So for any base topological space, I can define a functor. Let me call it maybe, I don't know. Okay, let it be, this is the name of this functor, P dot. So where P dot of n is P in power n. Yeah, so then I have to define these operations, right? Which is really easy. So then again, if theta is a map of finite sets from S to T, that means that I have for each I in S, I am given theta of I, which is subset of T, may be empty. Then I have to define theta lower star from P in cardinality S in the same direction. It's not gamma op here, it's gamma, it's covariant function to P cardinality of T, which is defined as follows, that theta star applied to P1 P S is x1 xt, where xk is pi if k belongs to theta of I, and xk is base point. So let p0 be base. Okay, let's start with the base point. Then it's star if theta of I is empty. Sorry. If k it does not belong to theta of I for any I. So, because we know that union of all this theta I, it's not necessarily entire T, so then it's not in the image of this map. Then we take the base point. And this, in fact, gives me, so this is better to denote by K, because N is a dimensional sphere. So then this gives me a factor from gamma op to top, which one can easily see. So then in particular now I apply it to P equal to n dimensional sphere. Then I have M, I associate n dimensional sphere in power M, and this assignment gives me a factor from gamma to top. And then now I define something like coend, as I said last lecture. So then if I have, so then A, it's a functor from gamma op to top. So P is a functor from gamma to top. Then I can define the joint coend, something like P tensor over gamma A, which is by definition the joint union of P n times A n over n. and then I take quotient by relation as I did for the realization, then for any morphism theta from S to T, for any element alpha in P of N of S, and for any beta in A of T, this equivalence relation says that theta lower star alpha beta is equivalent to alpha theta upper star beta. So the same way as I did for realization, and this is of course a sort of colimit, as I said yesterday in general. So it's particular colimit.
If you restrict it to delta, would it be the same answer?
If I restrict this to delta, no, of course not. No, of course not, because here you have more morphisms, you have more equivalent guys here, if you do it for gamma. Yeah, no, it's not really the case. So then, it's different from the same stuff in data. But general name of such construction is coend, and what we have to know now that it's sort of colimit, which is, I guess, clear. Yeah, so then actually the statement of Sigal is that Bn of A is Sn tensor A, for any A, in that sense. So I'm going to prove it in a rather elegant way. I have some sort of 15 minutes, and then I think it will be enough. So the proof which I'm going to present is different from Sigal, so I don't like actually Sigal's proof. It's not very conceptual in this place. So well, I use some ideas which I found in the paper of Anderson, written about the same time, based on unpublished Sigal preprint, but this is his own idea, so it was not in preprint. So well, I'm going to use something, a little bit of some categorical tool, maybe, which is called, maybe I first have some before categorical tool. So as you know, the simplest functions are unedder functions, right? So then I have, for example, for fixed n, I have such unedder function, and it's a function from gamma op to sets. Yeah, so then, for example, let me take n equal to 1. So then I have gamma to 1, and this is such a functor, and I'd like to consider its realization. So what is the realization? So the statement that it's a circle. So to have realization, you first restrict to data and take the realization. So the proof is as follows. So then, if you have here an arbitrary if you have arbitrary map in gamma from n to 1, then this map is necessarily factored through a map from 1 to 1. And here, through map 1 to 1, and here you have actually two maps from 1 to 1, where this element is sent to empty set or to one element of 1, so then those which sent to empty becomes degenerate in the sense of data, right? So then actually it means that when you restrict to data, you have only one non-degenerate simplex, and this is one simplex. So only non-degenerate simplexes when you restrict. So in I upper star gamma 1, it's a simplicial set, and you have here only one non-degenerate simplex which comes from in dimension 1. But what is important that if you have, for example, delta just a second, to 1, delta in this way, right? Delta to 1, right? Then you, of course, the realization of this is interval, right? It's in general, if you have realization of delta to n, it's a standard this topological simplex. delta n. But here, what is important, because here it's interval and these 2 points are not identified, because you in delta, you have 2 maps from 0 to 1. But in gamma, you have actually, this 0, it's empty space, which is initial object, like empty space usually is, and you have a single map. So then if you actually have not that, but take that and then restrict to delta, then these 2 endpoints become the same point, so then you should collapse them and you get circle. Because you make use of the realization of simplicial set, it's always CW complex, whose cells are non-degenerate simplices. I did not phrase it out, but well, let me skip it. It can be, you probably some people know that, right? So then if you have simplicial set, not simplicial topological space, then you have a CW complex structure on realization where I-dimensional cells are corresponded to dimension I non-degenerate simplices, because in the process of realization everything degenerate is collapsed to less dimensions. So well, anyway, it's like that. Okay, that's fine. So now let me consider, let me take more complicated task and ask me what this guy is. This is actually a bit more complicated. In fact, it's S1 in power n. So how to prove it? Actually, claim is the following, that in gamma, this is Anderson claim, that n is actually product in gamma, a product n times of element 1. So this can be easily proven. It's an exercise. You can do it. It's really elementary, but it's amazing that it's true that element n is a product of n copies of element 1. So then, if you consider realization of gamma n, then you can write that it's realization of gamma product of 1 n times, right? Then you can, this is limit, so you can put it in front of gamma, so as a, in front of gamma, so then it's product of gamma 1 n times, and then now you make use that realization commutes with products. So then it's product of realization of gamma 1, so n times, which is S1 in power n, because for 1 we already know. Yeah, it's some example of some categorical proof, I would say, which is very beautiful. But now I like to go a bit further, and I like to consider the following task. So then assume that I have, assume that I have actually the precomposition. I take gamma, like gamma op to sets. Here I have the functor gamma to 1, and here I have a functor from gamma op in power k to gamma, which comes from my nice functor from gamma to gamma to gamma, right? So then I take the composition, I don't know how to call it, and then I take realization of this function. So the question is what this realization is, and the answer is that it's k-dimensional sphere. And we can prove it quite similarly, because what we need to do actually, we take gamma of n1 times n2 times so on times nk to 1, so as poly-simplicial set. So then the same argument shows that as a k-simplicial set, poly-simplicial set, we have only that any map like that factor, so that any map n1 times nk to 1 in gamma factors through map 1 times 1 times 1, so k times. This can be easily seen in gamma. But then you actually make use the same argument. So then you have a product of k one-dimensional cells in the realization. But all this, so this is somehow a priori, in delta it would be k-dimensional cube. but making you the same argument that here where we consider boundary of this, we have actually just a single element. Yeah, so then we have, so if one of these ni is 0, only one, then we still have 0, and then it results that we have to collapse all face of this cube to a point, and then we have k-dimensional sphere. Yeah, and the same argument here shows that if we have now realization to n here and here, and 1 times nk, then again n is a limit of 1 n times, and we have sk in power n. Up to me it's very beautiful argument actually, so I like a lot. So the argument which Sigal provided with some computational, so in my opinion it's a great advantage of answer, to put it in this way. So now I can relate these nice computations to computation of realization, right? So then for example, yeah, so let me do it.
I'm confused that when you're coend, you have gamma and gamma op.
What?
In this coend that you wrote, you define the tensor product of these two functors.
Coend, right?
Were the two functors both gamma spaces, or was one of them gamma space and the other, I don't know, co-gamma space?
Co-gamma, because I said that the one which you associate with topological space is not
gamma space.
co-gamma, yeah. It's not gamma op, this I said. Yeah.
Okay.
It's in the same direction, you see, ST.
Okay.
Yeah, okay, good. Yeah, so then we can, for example, find the formula for BA, right? So it turns out that it's S1 in this sense. S1 tensor A, so then it means that BA K simplex is Sn simplex, it's N S1. Yeah, well, anyway, it's this formula, so then it's not that, but it's coherent, right? It's some formula in this sense for P equal to S1. So how we can prove it? Here we use some so-called Coyonnet lemma. Maybe we can form it in a bit different way, but well, this I found, well, I don't know, Anderson actually doesn't work with that because he does it in another setting, but I guess that this could be a nice statement that, for example, we can, for any an, we can write it like that it's circle, or again, coend, actually, we have it's actually for any category. If you have functor f from C to any category where, say, some very simple colimit exists, then we can not necessarily sets, this is important. Then we can write that this is actually the same, this f of this, it's actually coend of C n over Fn. So, and here for n in C. So we get, yeah, probably here I should write C op. Right. So then we have such formula, and this is also, no, this is actually very similar to Ionet lemma, but in fact the classical Ionet lemma also exists not necessarily to functors, to sets. It exists for any category in which limits exist, and this one colimit. So because colimits I need to define this guy, so this is a set, and then I have to, it's ordinary category, so then for any set S, and any object alpha object in, well, E, I define this guy is as product of S times of alpha. And then I have to know that it's actually, well, that, yeah, that it's, yeah, well, okay.
It seems like both left and right are contravariant. Is that correct?
No, here it's F is op.
So it's F is
it's over n. Here it's covariant and here it's contravariant.
In n.
Huh? In n.
In n.
And
Okay.
here it's a free. This is my formula.
Yeah, sorry.
Yeah, so then if I have A from gamma op.
So this in this tensor product, you write like we're supposed to write the same coin formula, but with.
So let me. Sorry, I'm sorry because I have just 3 minutes. You can ask your question after. Okay. 2, okay. So then I use it as follows. So then A like that, it's this coherent formula that it's gamma of this n over n in gamma, this A of n. And then only this factor depends on my free argument. So then realization of this, it's actually realization of this thing, right? Gamma n. This is actually co-limit somehow. This coherent is co-limit, so co-limit and all co-limits commute with realization. This I know, so then this is why I can write down this. Well, actually, this, yeah. So well, I write it down as realization of gamma n, and then I put co-limit here, and this A of n. In this coherent sense, right? So this is coherent, but here I have realization, and this I know to be S1 in power n. So then I get this formula for n equal to 1, and for general n I argue similarly, but I have to consider functors from gamma op times gamma op to gamma op, and then my A to top. So then I actually apply the same trick and make use that here I have sk in power n, here k factors. Yeah, so then it proves this argument. So this is actually a typical categorical somehow way of proving, which I think is very nice. And then, yeah, you use actually some commutativity with some limits, co-limits, and so on, and reduce to simple cases. Yeah, so up to all these co-limits which you can produce, if you need to prove something, which by co-limit generate many general objects, then you reduce to some simple object and prove for that. So this is an example of this argument. Yeah, so then actually, yeah, so then it follows actually, and then probably the last thing which I say today, that this is actually sk in this sense, tensor A in this sense. So this is actually the formula, and also we have, well, in fact, it's for terms of the spectrum, but also we have this map to sk plus 1, and little bit of further speculation can prove that this gives us entire spectrum. Not only terms of spectrum, but also the structure maps of the spectrum. So then actually this formula is made use by Sigal to construct the right joint, in that sense that home in spectra from this this spectrum which I associate to A, not necessarily even special, and here I have an arbitrary spectrum Y, it's something like in gamma spaces, arbitrary gamma spaces from A to some f of y. So this f of y we will find the next lecture. Hope that I should probably at 6 o'clock start my journey.
Okay, so let's take the speaker. So do you have any questions?
In the rightmost part of
Yeah.
my board, right? So this product is needed to define what this covalent means, right?
Here.
Да.
Yeah, да.
То есть это
Как по-русски, может.
вот эту лампочку нужно записать вот точно так же, только вместо декартового произведения там вот это.
Ну вот, да, понимаете, это как бы in general it's something like tensor and cotensor. So then in principle it's about the following stuff. Then, for example, you can consider, for example, simplicial category. So category. Well, I mean that I like to say that, for example, if you have a category, it might be simplicial category, meaning that you have for S simplicial set and Y object of your category C, you might have S times Y and home somehow from S to Y, which is denoted like that, which I again objects of your these two, I again your objects of your category C, and it should satisfy some. Well, and then there are so then this one should commute with all colimits by Y, and this should commute with all limits by Y. Yes, with all limits. Yeah, so then actually this is somehow, well, but I say that if S is simplicial set, it might be quite complicated. But if you like some this tensor and cotensor over set, then for this task it's enough for C to have some simple limits and colimits. So then any category with enough limits or colimits is tensored and cotensored by set. By tautological reason, when you define this thing as just a product of S times of Y, and this you define as home from some, well, actually you define it as this is co-product and this is as product of S times of Y. So then for any category you can define these tensors and cotensors over sets, and this only you need for that is this products and coproducts, very simple type to exist. But in our case, these gamma sets are finite things, so then S should be finite. So we need only existence of finite coproducts, which is very, very mild condition on the category, which certainly everything we work with fulfill. So then we need it to be some commute with all colimits by Y. So somehow this I use it implicitly, I guess, that it commutes with all colimits, right? Well, anyway, so then this is, I guess it answers your question. Yeah, well, if you're interested, we can discuss it. I mean, it's quite important to understand each particular part of this proof, because it's some nice pattern how such arguments work. Yeah, well, yeah, so this is Anderson. I forget, I guess D.W., right?
So I think if we have any other questions, you can ask these questions during the lunch time. So
Yes.
let's thank the speaker again.